The infrastructure of artificial intelligence is condensing. The massive warehouse-scale server racks that power modern AI are shrinking into single, glowing microchips on the network edge. For years, the industry has operated on the assumption that deploying artificial intelligence requires sending your data to centralized cloud clusters, running models with hundreds of billions of parameters. But routing high-frequency, narrow business tasks to these massive models creates a structural financial flaw. Every prompt incurs a metered cost, trapping enterprises in a cycle of runaway operational expenses, or OPEX, that scales linearly with their usage. Cost is only the first constraint. Pushing data back and forth to a distant server introduces P99 latency spikes. When a system requires constant network round trips, real-time workflows often fail under the delay. Then there is the data exposure. Routing sensitive enterprise records, financial data, or secure code outside a controlled network perimeter creates an immediate cybersecurity risk. Relying exclusively on centralized cloud AI to execute high-volume, everyday enterprise tasks is operationally unsustainable. The architecture is beginning to pivot. The engineering response is the small language model, or SLM. These models operate in the highly compressed range of 3 to 8 billion parameters, retaining robust logic while shedding the bulk of a frontier model. The deployment target for these SLMs is no longer the cloud. They are built to execute entirely on-device, powered by dedicated mobile neural processing units, or NPUs, housed directly inside laptops, smartphones, and industrial sensors. This forces a complete financial inversion. You move the compute burden from a continuously metered variable cloud expense to a fixed one-time hardware capital expenditure, or CapEx. Once the hardware is paid for, the operational outcomes change. Processing occurs with zero network latency, and the marginal cost of running 1 million additional queries drops to zero. Edge AI restructures the core unit economics of enterprise intelligence, decoupling growth from external API costs. This local execution is physically possible because of specific advancements in silicon architecture. Dedicated mobile NPUs are now shipping with the ability to process over 100 trillion operations per second, a metric known as TOPS. These chips rely on asynchronous mixed precision math. They execute complex tensor calculations independently within the NPU registers, leaving the device's main CPU cores available for other tasks. Bypassing the CPU for AI tasks reduces standard battery energy consumption by up to 85% during active inference. NPUs also utilize a unified memory architecture. The tensor cores tap directly into high-speed LPDDR5X RAM, which eliminates the data bottlenecks caused by routing information across legacy system buses. We can quantify this by benchmarking traditional CPUs against dedicated hardware accelerators running the exact same model. This chart tracks power efficiency. On the left, blue bars represent the CPU's heavy energy consumption. Orange bars show the NPU operating up to 40 times more efficiently. On the right, GPUs offer minor improvements. NPUs provide the magnitude-level efficiency required for the edge. Silicon architecture has successfully separated machine reasoning from the need for a continuous high-wattage power supply. Hardware alone only solves the physical constraint. The software challenge is taking a massive 70 billion parameter cloud model and algorithmically shrinking it into a mobile footprint without destroying its logic. The first technique is knowledge distillation. Engineers take a massive teacher model and use it to train a much smaller model, forcing the compact architecture to mimic the verified reasoning steps of the larger one. Next is 4-bit normal float quantization. Neural network weights, traditionally stored as precise 16-bit floating point numbers, are mathematically compressed into dense 4-bit integer blocks. This shrinks a 16-gigabyte model down to 2 gigabytes, removing 80% of the size with negligible accuracy loss. Finally, developers apply progressive simplification. Instead of asking the small model to perform every possible AI task, they narrow its required output scope. If you reduce a complex 7-field data extraction request down to a strict 2-field schema, you exponentially increase the probability that the smaller model will generate a perfectly formatted, reliable output. When you pair precise task boundaries with extreme algorithmic compression, localized software can match the accuracy of centralized models for specific routine workflows. The theoretical advantages are clear, but we can verify these claims by looking at deployment data across physical hardware platforms. One metric for industrial deployment is throughput density. This measures a device's token generation speed, normalized against the physical volume of the device itself. This surface plot visualizes throughput density. The dark purple peaks represent the M5Stack NPU dominating this metric, with 90,000 tokens per second per cubic meter. Compare that to the pale, flat region mapping the unaccelerated CPU. NPUs outclass standard CPUs in space-constrained installations. The second deployment metric is energy consumption, measured in megajoules per million tokens. This chart maps energy draw. The deep blue trough tracking across the GPU and NPU reveals an energy footprint of 0.5 to 1.7 megajoules per million tokens. Without acceleration, standard CPUs draw significantly more power for the exact same workload. But hardware efficiency is only half the equation. We have to map these hardware profiles against actual extraction accuracy. An accuracy throughput Pareto frontier shows where shrinking the model yields speed without degrading logic. The optimal point is a highly distilled 4 billion parameter SLM. It matches the exact match accuracy of an 8 billion parameter version, but operates 3.8 times faster. The benchmark data confirms that for specific enterprise workflows, localized SLMs outclass frontier cloud models in speed, physical footprint, and energy efficiency. The engineering benchmarks prove the architecture works. The next step is executing it inside a living business structure. To transition from theoretical AI capabilities to active deployment, we look to the TechView's 10X platform. You don't need a multi-million-dollar AI budget to automate your operations. At techviews10x.com, we teach you how to use lean, high ROI AI tools to streamline your workflows, grow your business, and generate revenue online. Check out techviews10x.com. Link is on your screen. The companies gaining ground today are the ones deploying efficient, localized AI implementation, avoiding the high margins of generic cloud APIs. Which brings us to a structural limitation of cloud AI, the difficulty of guaranteeing data privacy when information leaves the device. By executing tasks locally on an offline edge device, the architecture creates a hardware-level barrier between sensitive data and the external web. If the data stays on the silicon, there is no API request to intercept in transit. There is no cloud server log for a third party to subpoena, and there is no risk of your proprietary information contaminating an external training pipeline. This security extends to distributed cyber-physical systems. Whether it is an unmanned drone or a remote satellite ground station, local SLMs parse telemetry and make autonomous decisions, even when hostile jamming or weather severs the network connection. The consumer hardware market is preparing for this shift. 16 gigabytes of high-speed LPDDR5X RAM is rapidly becoming the baseline for mobile devices, laying the physical groundwork for local models across the grid. Hardware and software are converging on-device multimodal models capable of processing live vision, voice, and sensor fusion at sub-10 millisecond latencies, strictly offline. The industry is moving away from the default of routing every routine query through a central server. For high-frequency, narrow tasks, the economic and security advantage has shifted to the edge. Visit techviews10x.com and subscribe to TechViews 10x for the latest tech breakdowns.